Hello, everybody, and a warm welcome from my side to this webinar about extended SWIR spectral imaging technologies. And at first, I would like to give you an overview about the takeaways you will get during my presentation. I will try to give you an idea about what SWIR enables you to see and which sensor technologies are available for SWIR imaging, with a special focus on SWIR, on extended range SWIR sensors, or as we say, just eXtended. Thereby, you will also learn more about the strengths and weaknesses of different eXtended sensor technologies and what really makes the difference, especially for spectral imaging. And finally, of course, I would like to provide you a brief overview about the broad range of SWIR and eXtended cameras AlliedVision is offering. So let's get started. In this image, you can see three different substances captured with a visible light camera, or are just two. It's hard to distinguish, but actually it's three, namely sodium carbonate, citric acid, and sugar. They are obviously hard to distinguish with our own eyes or a visible light camera. So what can we do to get more contrast into the image? The answer is quite simple. If we shift the spectral sensitivity into the SWIR range, we can get more contrast. Thereby, we have used in this case a special version of our gold eye camera with VGA resolution InGaAs sensor that is able to provide images at simultaneously at different wavelengths that are named at the bottom of each image. And as you can see clearly at 1410 nanometers, these substances distinguish most. So you can imagine if you are using extended SWIR cameras, you have much more materials you can identify by spectral imagings. And let me give you another example. What do you see here? Yes, it's a lot of plastic, but how do they distinguish themselves in the SWIR range? To give you an answer, we need to look at the spectral fingerprint of different plastic types. As you can see clearly, they distinguish from one another at different wavelengths. And especially in the wavelength range beyond 1700 nanometer, which we call extended SWIR or just eXtended, as already said, you need more. It's possible to detect more, and you need special sensors to do so. So let's have a look at the spectral ranges of different sensor technologies. The electromagnetic spectrum has a broad range, much broader than shown here. And as we as a human can see only between approximately 400 to 1700 nanometers. Whereas silicon-based sensors typically used for imaging between 400 and 1000 nanometers, whereas near-enhanced CMOS sensors provide improved sensitivity beyond 750 nanometers. Depending on the sensor glass material and the internal sensor architecture, they can be optimized to sense down to 200 nanometers. These are then UV sensors. And nevertheless, at 1050 nanometers, even the near-enhanced CMOS sensors have a very low quantum efficiency at around 10% only. Therefore, other sensor materials are needed to detect light in the shortwave infrared beyond 1100 nanometers. The most popular SWIR sensor types are using materials as indium gallium arsenide, or just InGaAs in short. Such sensors are typically sensitive in the range from 900 to 1700 nanometers, but it's possible to make them sensitive in the visible range as well. To do so, you have to thin the indium phosphide layer. The indium gallium arsenide compound is grown on, so that the visible light can hit the photoelectric conversion area. And this is, for example, possible with the IMX sensors from Sony. The beauty of InGaAs is that they can also be manufactured in different compositions of indium arsenide and gallium arsenide. Such are known as extended range InGaAs, or as we name them, eXtended sensors. And at the end, the ratio between indium and gallium determines about the cutoff wavelengths of the sensor. This is the maximum wavelengths the sensor can detect light. And these sensors can be designed in different flavors. Typical are sensors that are sensitive up to 1.9, 2.2, or 2.5 and 2.6 micrometers. Another type of sensors is made of mercury cadmium telluride, or MCT in short, which is one of the most popular sensor types for imaging beyond 1700 nanometers in the SWIR range. And furthermore, there are type 2 superlattice sensors available. They are already well known for mid-wave imaging, but there are new material compositions available that makes them sensitive in the SWIR range as well. And the latest technology available are colloidal quantum dot sensors. They are often based on lead sulfide or graphene. And there was nowadays several options to image in the SWIR and X-SWIR range are available. And as you can see, InGaAs is a great material for imaging in the SWIR range with great flexibility. So let's now have a more detailed view into these technologies. On this slide, the diagram shows specific performance parameters of existing extended range SWIR cameras, their peak quantum efficiency, the supported spectral range with a quantum efficiency larger than 30%, the rating regarding how low the dark current is, and the sensor's resolution, pixel size, and cost level and dynamic range, as well as the frame rate. For spectral imaging, especially high frame rates and quantum efficiency are essential. So let's now have a closer look how the typical cameras with the already named X-SWIR sensors perform. At first, I picked here the colloidal quantum dot sensor-based camera. As you can see, its quantum efficiency and frame rate is not very high, whereas it scores with lower cost, lower dark current, and high resolution of 2 megapixel. The next camera is equipped with a Type 2 superlattice sensor, and this camera has a high dynamic range, as well as the smallest pixel size as SXGA resolution, but it also has comparatively low quantum efficiency and frame rates, as well as an extremely high dark current and high costs. Whereas the MCT sensor-based cameras with VGA resolution sensor supports the broadest spectral range from 400 to 2500 nanometer at high quantum efficiency, and its dynamic range is also at highest level in our comparison. Nevertheless, it's still an expensive technology requiring strong cooling that is realized via Stirling coolers to get rid of the high dark, or to compensate the high dark current of the sensor. Finally, our Gold-Eye SWIR camera with SXGA VGA resolution sensor. It has highest quantum efficiencies and frame rates, and appropriate spectral range and dynamic, as well as moderate dark current and price. Only downside, if you want to say so, is the very low resolution of the sensor which is VGA. So in summary, it can be stated that extended range InGaAs sensors are ideally suitable for spectral imaging beyond 1700 nanometers with great price-performance ratio. They are especially cheaper and much more durable versus cryogenic or Stirling cooler-based MCT cameras, which typically have a lifetime of only 3 years. Other sensor technologies with higher resolution as Type 2 superlattice or CQD sensors do not support the high frame rates, and quantum efficiencies like extended range InGaAs sensors do. So let's now dig a little bit deeper into this technology, and let me provide you some benefits of our Gold-Eye X-SWIR cameras. Gold-Eye SWIR cameras feature fast extended range InGaAs sensors with QVGA and VGA resolution and can sense up to 1.9 or 2.2 micrometers. The cameras are available with AlliedVision or camera link based compliant interfaces, and to reduce the dark current, the SWIR sensors are equipped with a dual-stage thermoelectric cooler. It enables to cool down the sensor up to 60 degrees versus the housing temperature, and thereby the integrated fan, as you can see here, enables an effective sensor cooling so that the sensor can be cooled down to minus 30 degrees. And besides that, SWIR cameras provide advanced image correction and processing features, as for example, non-uniformity correction and support for multi-region of interest control. Give me now 2 examples about the performance of these features. So in this image, you can see on the left side a raw image of an SWIR InGaAs sensor. You easily see here the typical cross hatches caused by the lattice mismatch between indium phosphide and indium gallium arsenide. But by applying our powerful non-uniformity and defect pixel correction features, such artifacts can be fully removed. As already mentioned, high frame rates are quite relevant for spectral imaging because they, for example, enable to operate conveyor belts at a higher speed, and where there was to speed up processes and increase throughput. To support this requirement, we have implemented into our Gold-Eye SWIR cameras a feature that enables to read out multiple regions of interest that we have marked here. And up to 32 regions or wavebands can be selected. Each is relating to a certain wavelength range. And with the multi-ROI enabled, only relevant data are transferred to the host. Therefore, the frame rate can be increased remarkably, as you can see in the table. And for example, when only 8 bands are selected, that each has a height, in this case, of 4 pixels, to distinguish certain materials or to identify certain spectral features, the frame rate can be increased by a factor of approximately 10 versus the full frame resolution. So now I would like to come to the application fields where SWIR cameras are typically used. Here, the most relevant is probably spectral imaging, like we have seen already today several times. And being able to detect beyond 1700 nanometers enables to identify and analyze many more chemical compounds and materials, which is useful in many application fields, as for example, recycling industry, to sort plastics or waste or clothing. But also in agriculture, it can be applied to do plant health monitoring and soil analysis. And spectral imaging plays a crucial role in various stages of mining operations, from exploration and prospecting to our environmental monitoring and resource characterization. Moreover, especially for art restoration and authentication, SWIR cameras can be helpful to identify the composition of paints and to see underlying structures. Both also helpful to prove the genuineness of the image or the painting. In the food industry, spectral imaging is a valuable tool for food quality inspection tasks, as package inspection or sorting and grading. And as you can see here, in this example, different types of contaminations are easy to visualize in the SWIR range. And as a last example, SWIR cameras can be applied to detect differences in chemical compositions of drugs to ensure their authenticity, as well as moisture-related issues in pharmaceutical products or packaging. And this is just a small selection of potential application fields using spectral imaging technology, but there are for sure other use cases for SWIR cameras. And for example, laser beam analysis, there are also medical lasers available that have a wavelength of around 2 micrometers, or in life science and biomedical imaging. Here you need to know that between 1600 and 1870 nanometers, the penetration depths in tissues is higher due to the lower scattering and absorption, and it's more or less the golden window for deep brain tissue imaging and OCT application, or optical coherent tomography. So at the end, I would like to provide you a brief overview about our SWIR camera portfolio. We are offering 2 camera series, the Gold-Eye sensor, Gold-Eye with sensors that have a tag, and the Allied for tagless sensors. These platforms host more than 12 different sensor types, as you can see here by the spectral diagrams, sensitivity diagrams of the sensors we are supporting. And we also support the new IMX992 from Sony. And we are supporting resolutions from QVGA up to 5 megapixel. And all these sensors are sensitive in the SWIR and in the this SWIR, as well as in the eXtended spectral range. Furthermore, we are supporting multiple standard machine vision interfaces as GigiVision, Camera Link, and USB 3, but also CSI2 or MIPI with serial range extenders based on GSML2 or FPD-Link 3 chipsets, often used for embedded vision. AlliedVision cameras are shock and vibration tested up to 30 G or 30 G and support an extended temperature range of up to 65-degree housing temperature. This makes them a very robust solution with high reliability, and that's why we grant 3 years warranty for high quality SWIR cameras.